Hi everyone, I'm Taylor, and I worked with Carlo and Bob on our project called Swinging for the Fences. We aimed to figure out how strikeouts and slugging percentage factor into a team hitting more home runs. To start, we needed data, and to start us off, we installed all the packages that we were going to need for our analysis. And then my first step in getting the data was to create a vector with all the team abbreviations that I would need to be able to pull the specific pages from Baseball Reference for each team. So all teams have their abbreviations in this vector. And then I created a for loop to call all of those pages for each team from the years 2015 to 2019 to be able to give us a 5-year span of data to use prior to the shortened COVID season. So that was this period of time that we used, 2015 to 19, and we pulled the batting table from Baseball Reference for all of these teams. Once we had all of the data pulled from Baseball Reference, we were left with tables that had some unnecessary header columns inside the table. So to remove that, we used this line of code where the rank column was only numerical values to remove those header rows that were duplicated throughout the tables for each team. And then to clean the data a bit more, we rearranged the team and season columns that were attached at the end of the table, and we moved them to the front of the table to just be able to work with the table better. And we knew we also had to filter the data. Our goal was to filter down the table to include all of the players that had more than 100 at-bats. This way, we would avoid a lot of the unnecessary zero values throughout our table and would help clean up our analysis. To be able to run this filter code on our batting stats table, we had to create a CSV of the entire table and then filter it off of that CSV. So this code is filtering out the at-bats data for any value that's 100 or more at-bats. Our next step after we got the data was exploratory analysis. So we wanted to visualize the variables that we wanted to look at and see how the distributions compared to each other and what they looked like. So here's a heat map showing home runs and strikeouts by team. So we have home runs along the x-axis and then strikeouts for the color gradient. And what you'll notice is as the home runs for teams increase, you can notice that a lot of the squares are dark red, meaning that those teams also had a large amount of strikeouts. Next, we looked at histograms for the 3 variables. On the top left, you'll see the distribution of home runs. It's skewed right, centered below 10. And similarly, you'll see the histogram of the distribution of strikeouts, which is also skewed right, with a center at about 50. And then on the bottom left, you'll see the distribution of slugging percentages, which is approximately normal. And what's interesting is that the strikeout and home run distributions both seem to follow the same sort of pattern.
Hello, I'm going to be talking about the distributions of the variables within our model. The first graph we're going to be looking at is MLB players' slugging percentage by season. Initially looking at this graph, it seems that the seasons with the lowest means were 2015 and 2018. Both of these seasons had a means of around 400, while all the other seasons had a mean of 413 or greater. 2017 and 2019 were easily the best years for slugging percentage, with the averages above 420 and both their upper quartiles being over 475. In 2017, I believe J.D. Martinez slugged 741 for the Diamondbacks, which is one of the extreme values I'm showing you right now. That's one of the highest slugging percentages I've ever seen, and is very impressive. In the second graph we're going to be studying home runs, MLB players' home runs by season. Again, 2015 and 2018 have the lowest means and upper quartiles, with 2015 having an upper quartile of 15 home runs and 2018 having an upper quartile of 17 home runs. This is less than all the other upper quartiles for the rest of the seasons. All the other ones were around 20 home runs, so that's just a very large difference between 2015, 2018, and all the other seasons. While 2017 might look like it's the best season because it's the tallest and it has the highest, statistically speaking, 2019 actually had the best season. The mean and the upper quartile for 2019 are both higher than the mean and the upper quartile for 2017. So just because it has an extreme value all the way and it looks taller does not mean statistically it is the best season for home runs for MLB players. For the last graph we're going to look at MLB players' strikeouts by season. 2015 was the best year by far, not even close, for not striking out. So this had an upper quartile of under 100 and a mean of 73. It wasn't even close. All the other seasons had an upper quartile of around 110 and a mean of around 80. So it wasn't even close that 2015 was the best year for this. This could also mean that strikeouts could be a useful predictor in our quadratic model that Bob created.
Thank you, Carlo. We started the linear model we made home runs the dependent variable, strikeouts and slugging percentage the independent variable. We ran that, and we first looked at what our adjusted R square would be, and it was 0.796. So therefore, about 79.6% of the variation of home runs could be explained by the linear combination of strikeouts and slugging percentage, which we felt was a large portion. The p-values were also small on these to intercept the strikeout and the slugging, so we thought we would go on from there. We ran the RMSE for that, and then we ran the residual plot. And when we ran the residual plot, we thought we did take a pause because we noticed a violation of the linear assumption here, because there was a pattern developing in the residuals and the scatter plot of the variables that showed a slight curve. So we decided to fit a quadratic regression model to see if that would fit the data better in the middle of it. So this was then our quadratic equation model here. And when we ran that again, we looked at the adjusted R squared, which was 0.1855, which was higher than the 0.796 from the linear model. So we felt better about that. Still low p squares for that one, except for the strikeout squared, which we removed from the model, as you can see here. So we removed the strikeout squared from the model and got still this adjusted R squared of 0.8152. So we felt good about that, low p squared, and then we ran that residual here again, and it was lower than the linear model. So we also felt good about the model there. And then finally, we did the plot of the quadratic model residual plot. And this time we thought there was less pattern. And then we ran the plot line for the fitted quadratic model here. You can see a nice straight line there on that. So basically, by checking everything, it looked like we had decreased some of that error in the linear model. So we went with a quadratic model for our project. In addition to the great plots we had made in R, we had wanted to show kind of what we learned in SAL 601. So we took some of the data from R, we turned in the CSV, and I created this in Tableau, which showed just strikeouts to home runs in the 5 years of data from 2015 to 2019. And I turned it into a tree map in Tableau. And as you can see, what we actually found pretty interesting here is that this kind of showed what we were looking for as we got to the conclusion that teams that actually had a lot of strikeouts, had the most home runs in those 5 years. The New York Yankees, the Baltimore Orioles, the Minnesota Twins, and teams that actually had the lowest amount of strikeouts, as you can see here, Pittsburgh Pirates, San Francisco Giants, Miami Marlins, all were at the bottom of the league. There's a few different, as you can tell, most of the red, which was lower strikeouts, are on this side. The one outlier, you have this outlier over here of the LA Dodgers, and you have a few outliers over here of like the White Sox and Tampa Bay Rays. But besides that, you can kind of see a pattern in this tree map. That led us to the following conclusion. How did strikeouts plus slugging percentage factor into a team hitting home runs? We found that there's a relationship between strikeouts and slugging percentage and home runs. That would kind of just show the major league teams that kind of hit the most home runs had more strikeouts and had better slugging percentages. The major league teams that had less strikeouts and lower slugging percentages had less home runs. So, and if a Major League Baseball, so how you would use that if you're a Major League Baseball team, you would probably say, let's teach an aggressive style of hitting and not be afraid of striking out, so you produce more home runs. And probably to further improve this model for a Major League team, we could raise that bat to over 30, so we could get kind of more everyday players, and also see if there's correlation between hitting doubles and hitting home runs, or hitting, so that something near like hitting to the gaps might be effective, or things of that nature, and pulling out that type of data and finding some correlation there. So that's what we found on this project. For Taylor and Carlo, I'm Bob, and hopefully Steve Cohen can use all that 400 million payroll to employ the three of us.